Hello everybody. So in this video we'll talk about 6.5, which is tree diagrams. These are helpful when working with probabilities, and so you can kind of sketch and understand what's happening. And we'll do two examples. So in solving many probability problems, it is kind of helpful to have these tree diagrams when you have various events and their associated probabilities. And for example, there is an event followed by another. So suppose that you wish to compute the probability of an event that results from performing a sequence of experiments. So there, as I mentioned, one following another. So the various outcomes of each experiment are represented as branches, right? For example, you have outcome 1 and you have outcome 2 and you have outcome 3, for example, right? And there is a probability here 0.5, this one outcome probability 0.2, and this outcome probability 0.3, so something like this. Then after this, there is some other event happening, and once you get outcome 1, you could go to two other outcomes. Let's say outcome A and outcome B, and each one, let's say this has probability 0.4 and this one has probability of 0.6. All right. So of course these trees are not going to be like symmetrical. They make or they may be. There is no rule except to understand what's the problem that is presented to you and graph it, and from there calculate it. So let's do this first one here. A quality control, a box contains 5 good light bulbs. And 1, 2, 3, 4, 5, for example, and 2 defective, this one, and 2 here. The bulbs are selected one at a time without replacement. So once you take one, and then there is less number left until a good bulb is found. Find the probability that the number of bulbs selected is 1, 2, and 3. All right. So if you want to look at this problem, let's clean now this. If you want to look at this problem, then maybe let's say you call this this outcome good light bulb and this one a defective one. Then you have a total 2, 4, 6, 7. So you have 7. So the good ones are 5 out of 7, right? So that's the probability of getting one from there. And getting a defective one is 2 out of 7. And so if you take like here, the bulbs are selected one at a time without replacement until a good one is found. So this, if you take one and it's not a kind of a good one, right? You still have 5, but without replacement, that means you have 6 remaining there. So the probability of getting that good one is 5/6, right? And in that case, for these here are going to be 1/6 for the defective one, because you took a defective one. And as you saw in previous work with probabilities, now the probability to this outcome here, right, is not a direct one. It's going to come from its sequence. So you will need to multiply the 2, right? To get there, you need to kind of 2/7 and 5, 6. So if we do 5, 6 times 2, 7, we get 10 by 42, reduced to 5 by 21. So the probability of this outcome is 5 over 21. And of course, this is a defective. And from there, we do the same thing again. Then the probability of the other is just going to be 1. And so the good is going to be 1 over 21, right? And how you're going to get that, of course, we do the same thing. Let's do it here. Let's see here the calculation of this one. So the calculation of this outcome is going to be 2/7 times 1/6. It's going to be 2 over 42, which is 1 over 21. So now we set up this tree diagram, and we're going to look into, I can't solve it, but let's answer the requests. For the first one, 1, the probability of getting 1, it's 5/7, right? And 2, it's going to be the 5 over 21, right? And for 3, it's going to be 1 over 21. All right, so the tree diagram here corresponds to that sequence that, of course, is shown in this figure that I did here. And of course, the probability is associated with the length of each path. So you want to see the path that you want, and you will find the probability of the outcome based on the length of this path, right? And we compute it, of course, by multiplying the probabilities of the branches. So this is a branch and this is a branch. And the first path corresponds, of course, to the situation in which only one bulb is selected. The second path corresponds to 2, and the third path is to 3. And keep in mind that we say that we dealt replacement there. All right. So let's look into another example. And this is a screening, a medical screening example. Let's get a little bit this darker. All right, so let's, if we want to graph this example here, it looks like we have, suppose that reliability of a skin test for active pulmonary, yeah, okay. Tuberculosis, yeah, pulmonary tuberculosis, right, TB, all right. Which, you know, it has to do with the lungs. So they have vaccines for them and stuff. And for some countries, they used to do some vaccines, maybe they still do up to now. So if you do a test, you could come up positive, but it's not, doesn't mean one has a TB. It could be because the person had a vaccine before. So it's important not to, you know, do multiple tests, not to activate these TB. So the other tests that usually are done is like X-ray and other stuff to double check. So let's look at this TB here. Of people with TB, we have 98%. So keep in mind, 98% TB, and let's just say no TB. Of people with TB, 98% have a positive reaction, and 2% have a negative reaction. all right? And of the free one, there is a 99%, and of course the other ones are 1%. So we can say positive and negative, and also here we will have positive and negative. All right, so let's continue. Then of course we'll talk about it again and explain and all that. So from a large population of which 2%, 2 per 10,000 person have TB. So 2 per 10,000 have TB, which means 0.002 have TB. If this 2 per 10,000 have TB, that means the no TB is 1 minus this number, right? Because that's the complement for the probability, which means 0.9998. A person is selected at random and given a skin test, which turns out to be positive, right? If it turns out to be positive, so that the 98%, which leaves this complement here, the 2%. Given a test which turns out to be positive, what is the probability that the person has active pulmonary tuberculosis, right? All right. All right. So what is the probability that the person has active pulmonary tuberculosis? We go back to the numbers that we're given, which is the 99% and the 1%. So 0.01, the 1%, and 99%. So now this tree diagram is complete. You can, of course, you can draw it, you reread, so it's kind of a cycle. You draw, you read, and you redraw until you get it correct, and you put the numbers on it, right? You put the probability and you correct the probability until you get your diagram matching the story. So the given data is organized in this diagram, and the procedures we'll follow. First, we're going to select a person at random from the population. There are two outcomes for this. So the probability that this person has a TB, of course, as I mentioned, is 2 by 10,000, which is 0.02, all right? For not having a TB is the other remaining okay. So for each of these possibilities, the possible test results, and of course they are conditional probabilities, and they are given to us. Multiplying the probabilities along each of the paths through the tree will give the probabilities for each outcome, right? So if you want to get, let's show it here. So if we go this way, right? Let's do on a calculator. If you do 0.2 times 0.98, then we get, okay, 0.000196, right? Okay, so you see it like we did in the previous example. And now you can do the same for the others, right? So if you come through these other branch here, and you come to 0.02 and you multiply 0.002 with 0.02, you should get 1, 2, 3, 4, 5, 4. All right. Then now let's show another one here, maybe with different colors. So if I come this way and I go this way, then the probabilities that we multiply there, 0.998 times 0.01 gives us 0.009998, and this one, of course, we multiply the same way, we get 989802. So the probability that the person has active pulmonary tuberculosis, all right, saying it a few times now that starts to work, right, is a conditional probability, of course. Has to be given that it is positive. It's going to be based on the formula. All right, and over that positive, and so we will add at the bottom the positive ones. All right, we have positive here and positive here, so that's the sum of the positive, right? And the intersection of the positive with the TB is going to be that 0.000196, which is 0.02. So the probability is 0.02 with a person with a positive skin test has TB. In other words, although the skin test is quite reliable, only 2% of those with a positive test turn out have active TB. So this is very interesting to understand, especially with now the coronavirus and the testing, and if you hear a false positive or a false negative, some stuff like this, you need to understand what it means. So in this case, although the test is reliable, a 2%, which is a small number of those with the positive results, those with the positive result has or have TB. All right. So these results must be taken in account when large-scale medical diagnosis tests are planned, because the group of people without TB is so much larger than the group with TB. The small error in this former group is magnified to the point where it dominates the calculation. And in this chapter, you will see a part about sensitivity of medical tests, which is the probability of a positive test in the presence of the condition. All right, and you should look at, and read it and understand it, because the positive and negative predictive values of medical tests can also be used to determine the probability of a false positive. As I mentioned, when a patient does not have the condition but has a positive test, or a false negative when a patient has the condition but test is negative. All right, and that's why sometimes you need to use another different method, or you need to use a second opinion or a different tests, because as mentioned here, medical screening, a screening is something, and diagnosing for sure is something else. All right, thank you.